Finally, the big day has arrived. The fundamental theorem of calculus. We can use it to find the exact value of definite integrals. No more approximating with rectangles or making a table of values. We can find the exact value. This is so exciting. We talked about the fundamental theorem of calculus in section 5.5, looking at some applications. But now we can actually use it to evaluate. So we said, if we have our derivative function or our integrand has to be continuous, meaning there has to be defined for all values on the interval from a to b, then if it is, we can evaluate that definite integral by plugging in our limits of integration into our original function f. And that's what we've been spending all this time on, finding, all that time in section 6.2, finding that function. Then we can plug those values in. So when we're going to do these, we're going to write an in-between step that's not seen when they just state the fundamental theorem of calculus, but it's basically what we're going to plug those limits of integration into. Okay, so first thing we're going to do is we're going to find our antiderivative function. Okay, and then we did this a little bit with derivatives. We put the bar, and then we put, with derivatives, we would put the x value that we were going to plug into the function. Now we put our lower and our upper limits of integration. So we know that's what we're going to plug in. So then we would say, okay, we're going to find f of b, upper limit minus the lower limit. So it'd be f of b, plug it into this function, and then plug in a, and then subtract. Okay, so let's look at an example. All right. The definite integral from 1 to 5 of x squared, which basically, remember, we'll evaluate out to be a number. It could be positive, it could be negative, it could be 0. All right. We know it would basically represent the area between the graph of x squared and the x-axis, because x squared is positive on the interval from 1 to 5. But how do we calculate that area without doing the rectangle approximation? Okay, so first thing we do is, what's the antiderivative of x squared? We can use our power rule, so that would be x cubed divided by 3. And then we're going to evaluate that at 5 and 1, and then we're going to subtract. Okay? So here's what it looks like. I'm going to go this direction. All right. So you have to be careful. You have to find each function value before you subtract. All right. So that means I'm going to replace the x with 5. So I have 5 cubed divided by 3. And then I'm going to replace the x with 1. So I have 1 cubed divided by 3. And then I'm going to subtract. So this is basically my f of b, and this is my f of a. And then you evaluate those, and then you subtract. So I end up with 125 over 3 minus 1/3, which is 124 over 3, or what's that come out to be? I think 41 1/3. Okay, so if you're a visual person, here's what we're looking at. Here's the graph of x squared, and we're talking between 1 and 5. So we're finding that definite integral is giving me this area. So we're saying this is the area of that shaded region. Pretty cool. Now, are you wondering why I don't have that c in here? Notice how my constant of integration, there is no c in here. All right, well, I'll show you why we do not need c, the constant of integration, when we evaluate a definite integral. Okay, so let's look at an example. So if I say, okay, what is the definite integral from 1 to 4 of 2x dx. Okay. Well, if I find my antiderivative of 2x, which is going to be basically x squared, 2 times x squared divided by 2 plus c. Okay. Using the reverse power rule. And then here's 1 to 4. Okay. So I'm going to include the c this time because I want you to see what will happen. All right. So these 2's will divide out. So I basically end up with x squared plus c from 1 to 4. Okay. So so I'm going to plug in the 4. So I get 4 squared plus c minus 1 squared plus c. So I've got 16 plus c minus 1 minus c. So if I distribute this subtraction through, then here's what happens. Okay, now what do I get? I get 16 minus 1, which is 15. And what happens here? I have a positive c and a negative c. Those will cancel out. So I basically am left with 15. So that's the reason why we do not need the c when we do definite integral, evaluating definite integrals, because they will cancel out. All right. Okay, so let's do another one. I want to find the definite integral from 4 to 8 of this function. Okay, first thing is I need the antiderivative. So we use our antiderivative rules, or basically our reverse power rule for the most part. So x cubed's antiderivative is x to the 4th divided by 4. X would be x squared divided by 2. And 1 is a constant, so that would be plus 1x. And I'm going to evaluate that at 8 and 4. So just be careful with your substitution and use your calculator to evaluate. So this is 8 to the 4th over 4 minus 8 squared over 2 plus 8. So I took that function, I substituted 8 in for x, minus, now I'm going to plug the 4 in. So it becomes 4 to the 4th over 4 minus 4 squared over 2 plus 4. Okay, so you've got to make sure that you get these expressions down to one single number before you subtract. Okay, so this should become 1024 minus 32 plus 8, which simplifies to 1000. Okay, over here, this is 64 minus 8 plus 4, which should simplify down to 60. Now I can subtract. 1000 minus 60 would be 940. So my definite integral evaluates out to be 940. So it looks like there's more area above the x-axis than there is below on the interval from 4 to 8. It could all be above. We have no idea without doing the graph. All right, how about if we have our integrand has e to the x in it? All right, we've done that, we're good. All right, so if I find the antiderivative, I'm just going to keep my constant 6 and then find the antiderivative of e to the 2x, which is e to the 2x divided by 2. Okay, and I'm going to simplify that here because I can fix the 2 and the 6 are going to become 3. So that becomes 3e to the 2x from 0 to 1. Now I'm going to substitute in. So I get 3e to the 2 times 1 minus 3e to the 2 times 0. So that's 3e squared minus, what happens here? This is e to the 0, which is 1. Okay, so anytime you have e to the 0, you're going to replace it with 1. 3 times 1 is, oops, 3. Okay, now you're wondering, what do I do with that e? What happens? Okay, well, it depends. If you're asking for the exact value, then you don't want to put that in your calculator. You leave it in terms of e. So exact value, this would be your answer. Or if you wanted, you could factor out the 3. It just depends, preference, I guess, in terms of evaluating it or what you're doing with it. Okay, so be careful on instructions. Exact value. Do not put a decimal approximation. Okay. All right, let's do one more. All right, so here I'm doing the definite integral from 1 to e cubed of 1 over x. Okay, we know that the antiderivative of 1 over x is natural log of x. And we need our absolute value bars around x because we have to ensure x will be positive. Okay, we're going to evaluate that at 1 and e cubed. Okay, so when I substitute that in, I have the natural log of the absolute value of e cubed minus the natural log of the absolute value of 1. Well, I know that e cubed is positive, so the absolute value of e cubed is just e cubed. So that's really the same as the natural log of e cubed. So remember, natural log is a logarithm base e. So this is going to evaluate out to be 3. Okay. Let's make a note of that. If I have the natural log of e to something, okay, it's always going to be whatever is in the exponent because this is the log base e of e to the something. Okay, so you're saying e to what power is e to whatever that is. So they have to be equal for these expressions to be the same. So whatever's in here, there's some stuff in here, that's what it's going to evaluate out to be, whatever that is. Okay? Because natural log and base e, remember, are inverse functions. So that becomes 3 minus the natural log of 1. So once again, if you're asked for exact, here is your exact value. Oh, wait a minute. Wait, we can do one more thing. What's the natural log of 1? That's actually an exact value that we do know. The natural log of 1 is equal to 0. Okay, so that's another thing to keep in mind. The natural log of 1 is 0, and e to the 0 is 1. Remember, they're inverses. Okay, so actually we could go one more step. So that would be 3 minus 0. That would give me an exact value of 3. So one quick comment here. You might see a problem like this in the book, and it might look like this. They might say, okay, the definite integral from 1 to e cubed of 1 over x dx is equal to just the natural log of x from 1 to e cubed. So you might see it where there are no absolute value bars there. The reason they can get away with that is because both of these numbers that I'm going to plug in for x are positive. So I'm guaranteed that I will not be taking the natural log of a negative. So if you know that, you don't need the absolute value bars. Or sometimes they don't put them on indefinite integrals because you're not going to be substituting something into it. All right. Good luck with your evaluating definite integrals.